Hello, we are back to continue our lecture on clip number 26, which is a continuation of what the previous clip number 25. Okay, that let me go back to okay. This is the last uh, kind of last slide that we finished to that we talking about the simplex method in matrix form with the reduce the formula for the reduced cost coefficients and also uh, the general idea of the simplex algorithm uh, and also the weak we discussed about weak and strong dualities in metric form and end up having the strong duality that can help you to find the dual solution simultaneously after you find the optimum primal solution. Okay, so today we're going to continue with this slide that we will study and consider the case of linear programming with too many constraints. What is too many constraints mean is that let me go back to the original form in the metric form. If you have an constraint in terms of equation, certainly you need to have this condition. This means that the number of constraints have to be less than the number of decision variable. Once you already convert all the inequalities to equation, okay. But in this case, we talk about when m is much larger than n, okay, which will not fit with this condition, okay, but it will fit with this form, okay, which means that if you be able to convert all equation and all into an equalities, okay, you end up can have this situation, okay, that when the number of constraint is much larger than the number of decision variable. How do we tackle or handling solving this type of problem? Okay, it's summarized in this what appears on the screen now. Okay, initially let's go back to this formula. Okay, you have A, which have m row and n column. Okay, with m is much larger than n, and all of them is in the form of greater than or equal to the right hand side. Okay, so initially we start with a much smaller submetric within A. We call this A palm with the size of P by N. Okay, with this decomposition of A to a part of A palm, okay, B have to be decomposed also. Okay, it's a subvector within B corresponding to the same row as the A pi. Okay, so we have A prime and B prime. Okay, just contain only P row. Okay, for within metric A and within vector B. Okay, and P is certainly much smaller than M. Okay, much smaller than M. And then we start solving the original LP by considering only the constraint related to A palm and B palm. Okay, so actually this is your main problem. You solve only a partial problem here. Okay, suppose that you say that X star is an optimal solution for this system, this subsystem. Okay, you use this X star optimal solution checking with the whole system, which is A times X star minus B. Certainly, the content of A prime within A is always feasible, which means that AX star have to be greater than or equal to B. But for the remaining part in A, which is excluded from A prime, okay, within A, you don't know, okay. Since this is the all we transform all the inequalities to greater than or equal, okay. Uh, if suppose that A star minus B, okay, we try to identify the element within this vector that has the smallest value, which means it can be minus a large number. Okay, if the value is negative, okay, it means that it's infeasible. There exists some constraint that not including in A palm, okay, that is infeasible, okay, okay, which means that A times X star, there exists some element of A X star less minus B less than 0, which is violation with the constraint greater than or equal. Okay, and we pick the constraint with the smallest value, which means the most violated constraint. And we add a new row, p equal p plus 1, right? Add this constraint, okay, the constraint uh, which gonna include the left hand side and the right hand side, to the left hand side to the A palm and the right hand side to B palm. Okay, so A palm and B palm, the size of P increased by 1. And then we repeat the process, solving the problem again. And then we solve the problem again, we get the new X star. And then in the next iteration, we check again with X star, AX star minus B. And we keep doing this process as long as the smallest value of AX star minus B still have a negative value. Okay, because it's still infeasible. So you need to add this as a in technical term we call a cutting plane. Try to find a new solution that help you to resolve this violation. Okay, and we repeat this process until the smallest value is greater than or equal to 0, which means that once you be able to obtain X star such that A times X star minus B, okay, the minimum value is greater than or equal to 0, which means that all constraints had been satisfied. Okay, but you might think about this, that the worst case that can happen, that if you keep adding until uh, p is equal to m, that's the worst case, because if p is equal to m, it means that you solve the full model. This approach won't be any efficient. Okay, and it will take you much longer time. Okay, but fortunately, this is not such a case in many applications. Okay, this approach can help you savings solving a large scale problem by solving a much smaller scale problem and keep adding the size of the problem. And we hope that the final iteration, the size of a palm is not still much uh, less than the size of p is still much less than m, which means that you don't need all of the constraint m constraint in the model, because you only have n, which is much smaller than m. Okay, if you might try to recall the idea of in metric form. Okay, because the optimal solution will be in a b inverse b, and the size of b is the size of m by m. Okay, okay, so in this case it's going to be a very large scale, because you have, but also contain a lot of zero, because once you add uh, convert this inequality to equation, there will be so many surplus variable, and you can say that at most m surplus variable, which means that's full scale problem. Okay, so the b, uh, many column in the b matrix here, okay, over here, okay, will contain a lot of kind of 0 0 1 0 0 0 kind of identities, column vector in the identity matrix, okay, of psi m by m. There will be only a few, at most only n column, which is much less than m, that have a kind of dense, it become a dense vector, which means that not many zero. okay, but fully the non-zero element, okay. And we just hope that we don't need to add all of them, okay. We will add at most, should not be much lesser than n also. No, not much more than n, that much, okay. So in summary, okay, this is the idea that we repeatedly start with a small scale problem and adding the size of problem one by one by considering the violation of the remaining constraint while solving the sub problem. Okay, and we stop when we found that the optimal solution, all the remaining constraints become what we call redundant. Okay, it's automatically feasible. Okay, okay. So when we know the idea here, we how we attack these too many constraints. Okay, we're gonna illustrate you with this example. Okay, again, this is the five of the problem. The problem LP with too many constraint variable. Okay, here is certainly contained within the folder of lecture 3. Okay, this is the file of the this one, the problem LP here. You can download here. Okay, and but this one we already download here. Okay, I set up a problem with these two generator. Okay, the first one is a constraint coefficient, the left hand constraint coefficients generator. We're using the smallest value of 1 plus 4 times uniform random variable. Okay, and we round the number to 3 precision digits. Okay, so this is the value. Okay, we generate. Okay, at most 3 digits. Okay, I mean, I gave you this formula so that if you can want to continue generate or deviate the problem to different size in both terms of number constraint and number variable, you can do it by using formula here. And the right hand side generator is start with 45 plus 5 times uniform random variable. So also we have a 3 digits number precision. So this is the right hand side generation. And this one is already solved using the open software here. Okay, okay, you can put the model in here. This one we didn't put it in here, but I will tell you a little bit that this group is what we call the changing cell here. Okay, okay, here this one is decision variable, the changing cell. Okay, they show different highlight once you solve it. Okay, okay, so this is the optimal solution, and this is the optimal objective function. We have 8 decision variable. Okay, and I'm gonna try to cut some of the color out. Okay, so that you can look at the real optimal solution here. This is the value of x1, x2 to okay, this one x1, x2, x3, x4, x5 to x8. Okay, and this is a c. This is the cost coefficient c. This is a c transpose. Okay, this is the x transpose. Okay, with only size of 8 by 1. Okay, but we as you know that now n is equal to 8. What about m? Okay, m can, this is the A matrix. Okay, and we already generate a problem. So quite a large file because I've set up this problem to become very large. You can see the resulting solution here. Okay, we have 25,000 constraints. Okay. So this generated problem fit with the definition of the problem that we are trying to solve here. Okay, because we have LP with 8 decision variable and 25,000 constraint. Okay, so then we will assume that AX over here, which is some product between this one, some product between this row and this row. Okay, and then you can fix the address here and get the formula here, and then you make a copy. Okay, the right, and this one is a times x, which is the left hand side. Okay, what's going on? What's up here again? And this is the right hand side. Okay, I don't know why this one here keep popping up. Okay. Oh, okay. Here, this is all right. So the condition have you have over here all the 25,000 rows, okay, of left hand side greater than or equal, okay, row by row with the right hand side. Then, okay. So it's quite obvious that you want to make this cell as minimum as possible by this is your decision variable area. You want to allocate, okay, the value to the positive value greater than or equal to 0 of all 8 decision variable that satisfy this condition that the left hand side need to be greater than or equal to the right hand side. And this is the optimal solution. It's not a little bit less than 32, but it's 31.98883818. Okay. And we're gonna try to solve this problem, but you know that we already use solver to Excel open solver to solve, and it can be solved not that bad, pretty quick also. Okay, because you have only eight column, okay, to generate. Okay, you will see that when you in term of problem setting up within the open solver, it's more sensitive when you add more variable. Okay, I mean it will take longer time. Okay, in this case, even you have only eight column, but one column contain 25,000. It's a lot of number, but I'm not running it for you because it gonna waste the time for lecture in this script. So, but you can go ahead and try it yourself and observe. Okay, and observe the behavior. Okay, so but we're not gonna try to solve this one just a benchmarking that we already solved the optimal solution, but we will try to use this approach, okay, the approach that we mentioned about this to solve this type of problem. Okay, first of all, I make a copy of this all of this to become a working, okay, a working area. Okay, so this is exactly the same number, but just leave the value here. We haven't allocate any value and the objective function, but all the formula in over here. So now since there's no allocation of x1 to xs, all the left hand side is less than or equal to 0. Okay, and it's certainly the maximum value is, you know, that this one ax minus b, right? Ax my no, it's b minus x ax. Okay, right hand side minus left hand side. Okay, this one minus this one. So the maximum value have to be 50 certainly, because based on the function generator here, you know immediately it's 45 plus 5 times random and rounding with 3 digits. Okay, so it's not going to be exceed the 50 value, and the minimum going to be within have to be 45. Okay, so this is another additional working area. Okay, this is we add these two column and a specific here. Okay, okay, certainly the max 50 is coming from this formula. We find the maximum value of the vector. This is the vector of, we call, in this case we compute b minus ax. Okay, but in the over here we check ax minus b. So all the rule have to be reversed, right? This one is if b minus ax, instead of choosing the smallest value, if you choose vector b minus ax, you identify the largest value. Okay, and when you repeat the process until the value is less than or equal to 0. Okay, if you instead if you conversely consider vector b minus ax instead of ax minus b. Okay, so we add these two columns. Okay, first of all, this one is b minus ax. Okay, and this one is just to check whether where is the maximum value is. Okay, okay, so this one is not is still the violation. I mean, this one, all you can see that all constraint is violated here because the left hand side is only 0, but you want the left hand side greater than or equal to the right hand side. So the star here just checking that this is a violated constraint. But the most violated one, you know that this is a violation only 49, 49. But the largest one, we already used this cell to compute the formula. You know 50. But where's the 50? So we add another statement here. We match the maximum element with other element within this vector. They start from AD4 to AD 25,003, which is all the element within the b minus ax. Okay, and then we there's no have to be precisely there's the attribute of 0 here. So in this one, okay, 7216, they will check that okay the location of the maximum value is at the 7,260. Start counting from here. We can estimate a little bit because we add this 3 low, right? It becomes 7,219. Okay, that would be the constraint that have we can reduce it here or shrink it down a little bit to okay to take a look at here. Okay, if we shrink down this side, okay, in this one okay, we're gonna do this one 7,216. Okay, so we go to constraint of 7,260. This one, okay, this one 7,216 is here, and you know you'd see here that it's it has the largest difference 0.50. This is the constraint that if you consider all variable is set at 0 value, the most violated constraint is here. It's a constraint number 7,216, and you know with the value of 50. Okay, so this one is a kind of working area. Okay, working area for what? To be able to identify a new constraint, a violated constraint. But before you getting all of this, okay, you go back and look at the procedure that we propose here. We have to initially start with some submetric and subvector of the right hand side, submetric for the left hand side constraint coefficients. Okay, so we develop this is a consequence sheet of sheet 3. Okay, we're gonna start to only the first 6 constraint only. This one is like p is equal to 6, and this is the A matrix. This is the left hand side and the right hand side. So go back to the original problem, which contained 25,000, right? 25,000 constraint. Okay, so we pick only the first 6 constraint here, the right hand side. Okay, with 6 right, to initially start with this problem. Okay, and then you don't even need to use the open solver because the size of the problem, you can directly use the solver here. Okay, and from all the formula that have been connected, okay, we want to, this is our target cell. Okay, E3 is our target cell. You want to minimize it by changing the variable cell. The variable cell is over here. machine, all the 8 variables. Subject to constraint, okay, this one is going to say the left hand side, 8 times x must be greater than or equal to, this is the right hand side. Okay, so we just press OK. And you know that this is the linear programming, so we can apply Simplex LP here in the solver routine here. Okay, then we can solve the problem. So, okay, this is what they find. Okay, this is the first solution that you found. This is an X star here. But it's satisfied for only 6 constraints. We still don't know whether the remaining from constraint number 7 to 25,000 if this solution is feasible or not. How can we do that? Okay, we can just easily copy this solution here and go back to sheet 1 and look at this working area here. That's why we design this as a working area here. This is a benchmark solution, okay, and we're gonna paste the value here, okay. This is so do we have the new x now? Not all x is 0 anymore. Certainly the objective here is equal to here. And you know that because we kind of cheating that we saw already see the optimal solution here. This is the minimum value for all 25,000 constraints. So you know now the solution from this 6 constraint, there are going to be some infeasible constraint, okay, or violated constraint. Because if this is already the optimal solution, these two values from here from R3, okay, let's say what it should be equal to E3, okay. So with this formula, they recompute the new say times x, the new check with B, okay. Now they're gonna check this is infeasible, okay. But you can see that the first 6 already feasible because certainly in sheet 3 we already solved it. We already it's guaranteed that this have to be feasible. So the first 6 are already feasible. But some of them, the remaining feasible, but still many infeasible left here. Okay. And from this, the difference between left hand side and the right hand side, okay, we pick the largest one here, 32. But where is it? We cannot just go in here and take a look at that. But with this match function here, help us to be able to identify that this maximum value along with this vector is in constraint number 13,737. Okay, so we can shrink down the size a little bit. Okay, with this, you know that the location is 13,737. So we move down to 13,000, right? Oh, let's go back again. 13,13737. So you look at the constraint number 1. Okay, 13737. Already passed. Okay, over here. This one. Okay, this one. 1330. And now you know this is the maximum value is here, 32.3. Okay, and with this is the most violated constraint in terms of the different measured by the difference between the left hand side and the right. So you now know that this is constraint is infeasible and has the most violation difference between left hand side and the right hand side. And next step, you want to add this constraint to this problem. Okay, you can put it the constraint next here, but it's gonna take you some time to recompute the add the formula and also change many of the left hand side formula. Okay, you need to add one more constraint down here. Okay, but it would be easier if you just adding it between just like this. Okay, I'm going to insert the new column here. the first original 6 here. Because one, if you add something over here, all of this will be automatically, okay, and also the objective function and anything, okay, can be automatically updated, okay. And okay, you know that you want to make a copy of this, okay. So this is the value you want to, okay. So these are coefficients, okay. So make a copy here, and then we just put it in here. So this is the new constraint added, okay. And with this formula, okay, you can just put it here, the 17, and you can go back to sheet 1 again, and this is the corresponding right hand side, okay. Just make a copies over here, then you get the right hand side here, okay. This is the right hand side, and you know that this is infeasible. All the constraint, the original 6 is already feasible, but this one have to be the infeasible constraint. We add this, okay, and then we resolve this problem again, okay. And one nice thing is that you don't need to update anything on this, because it's once you insert a new constraint within the remaining range, okay, all this the range is automatically add this, okay. When you have this, when you need to input this constraint range in Excel, okay. So everything all set, we control that all the changing cells become non-negative, so we solve it, okay. You can see that when you add more constraint, okay, this is additional constraint, okay, you might highlight it, okay, to make sure that, okay, this is the additional one, not the original that you start, okay. So this is the additional constraint, so we add a different color to either a little bit, or maybe green, okay. Oh no, green is the same as the left hand side, so we're not gonna do it, okay, here, okay. And this is also this one, okay. So this is the new, and you know that the objective function moving up to 18.751, okay, because you add more constraint, the minimum value increase, okay. And then the first iteration finished already, right? That, okay, you have the new optimal solution here, okay. And again, within the idea of this, okay, we repeat the process again. Why we need to repeat the process again? Because we need to check here, okay. So first of all, we make a copy of this solution first, okay. I'm gonna copy this solution, and then I'm gonna check it with this working area, okay. Okay, I'm gonna put the new solution here, okay. We paste it down, because once you get the new solution, certainly you get this is the new Z, but you have to check whether there still exists, there still exists the new, because the maximum violation is still 28. What you when you be able to finish it when this maximum value becomes 0 or less than 0. But this one, you know that the most violated, the difference between the left hand side and the right hand side is 28. The absolute value is 28.340. It's happened in constraint number 7181. Okay, 7181. So we go check a look at this. We constraint 7181. Okay, 7181. Oh, it's already exceeded. Oh, okay. This one is 7181 here. Okay, and you can see that the one that have the most violation, the 28 value is here. Okay, so we're now ready to move it here to this sheet 3 again. So we just insert a new row, okay, over here. Okay, and then we just make a copy of this. Okay, and when we come here, it's already have the background. We paste only here. Okay, there's only one. And certainly this is the okay the one, the computation. And you go back to sheet one. Okay, to sheet one. This is the left hand side, or the right hand side is 49.824. Okay, so we go here. Okay, 79.824. Oh, but this one is not, should not, let me check again there. Should not be 71 point. Oh, it's the same, right? 71.824. Because this one is the same as the right hand side is the same value as constraint 13,737. We can go and check 13,000. Okay, 737. You can see that they have the same right hand side. Okay, the right hand side is the same. The new constraint identified here, okay, in the at the top here, 7181. So we look at the constraint 7181. Okay, once you know 7181 here. Okay, the same 49.824, right? Okay, they have the same right hand side. Okay, so this one constraint. Okay, and I think that I make too much copy. Okay, we can just clear the content here. Okay, so now you have additional constraint. Now you can resolve this, and you can expect that the C keep moving up. Okay, so we can solve it again without any. You don't need to re-input the constraint again, because it's automatically add this additional constraint for you once you insert the constraint within the range of the previous constraint. Okay, so you solve it. Okay, now it's move up to 40 or to 20 value. But from sheet one, you already know that. Okay, uh, the true optimal solution is here. Okay, it's right here, 31.988. So you still know that this is not still not, you need additional more constraint, but you can now copy the new solution here. We copy here, and then we put it in here again. Okay, okay, we just paste the value here. Once you get here, the new objective, see, you have the new violation row. Okay, this one will become, as you can see that the resulting difference between left hand side and right hand side keep, the maximum will keep reducing, okay, to what we expect, that it reach the zero value or less than zero value. This one happened in the row or constraint number 10,317. Okay, okay, and this, I'm going to do this as a last iteration for you, but still not the optimal solution. Now we move to 10,317. 10,317. 10,300. Okay, 10,317 over here. Okay, so this is the one that have the most violation. Okay, okay, over here. Okay, so now you know, you just add this constraint. Okay, yeah, you have 7,000. Okay, you can insert the new constraint here. Okay, and you can just this one 10,370, just make a copy and then you put it in here. Okay, no, you need to press this number. Okay, okay, we're gonna shade it again using this. Okay, and then now you can move here. Okay, compute the left hand side. Okay, and this is the left hand side 49 point. Okay, we just make a copy 49.108. Then we'll move to this cell 49.108. Okay, so this one is a new constraint. And certainly it's infeasible because left hand side is less than right hand side. But we want left hand side greater than the right hand side. So we need to compute for the new solution. Okay, again, automatically added, so we solve. Okay, so you might see quite different because the previous one is 20.40, right? This one is only once you solve it. Okay, we try to solve it again. Okay, it sometimes you cannot expect they're gonna keep moving up all the time. This one is increased also, but increased very little. Even though we pick the constraint that we has the most violation that we been measured by the difference between left hand side and the right hand side. So a larger difference doesn't mean that the most improved for the C to the target value. Okay. Okay. Let's do it one more time. Okay. For so that you can work it out by yourself. That so we're going to make a copy of this one and go back to sheet number 1. Okay, and then here we got paste the new value here. Okay, you get this one, and this the new valuation is row constraint 8487. Okay, so we move now to constraint 8487. 8000. Okay, actually one way you can do, you can move it here. Okay, you just you want to go to AD. Okay, and you know that it's a constraint 8487, but you start from here. You so need to add the initial 3 row before we just start counting here. So it's gonna be 8490, right? 8487 plus 3. So we go to the column AD of 84 80. Oh no. Oh no. 8490. Sorry. So we go to this one. A D 8490. Okay. So now it can help you to reach the point faster. Then. Okay. Okay. We know that it's in here. So this one 847 is over here. Okay. So in sheet 3, we can increase this, insert. Okay, the new row here, and then you know the location here 84 87. Okay, so I'm gonna make a copies and then we add it here. Okay, 84, oh no, come on, different location. Okay, over here. Okay, and just shade the color and computing the left hand side, and then we took the value of the right hand side over here. Okay, we make a copies and then 49.2.3. Okay, then we just shade it. Okay, so this one we just resolve the problem again and then we solve it. Now I move to 8021 already. Okay, so you keep again next time you'll be able to write a kind of Visual Basic, you can keep do it as a VBA macro. Okay, and but I already solved this problem before, so we're not going to do all of this because we have two different files, okay, in your lecture 3 folder here. One is a Excel problem that we already show you. The other one is a solution, okay, the file that contains the solution. Okay, and we already opened this file here. Okay, huh? I erase it. How come? Okay. So I need to reopen it again. Okay. For me, no, I'm not using the that one. We're gonna do this. Okay. LP with too many variable. Okay. Okay. Uh, over here. Okay. This one is it's a already solved problem. The solution is here. You remember sheet 3 from the problem? Okay. The problem we already solved. We illustrate to you around 4 iteration here. Okay. But in the file of solution file, okay, over here, okay. Certainly in sheet number 2, this is all. You can see that this one we already include 10,000 and some the familiar, you know, the first one 13,000, 13737, 7181, and all of this. Okay, so this is the solution, the optimal solution that contain, you can see that how many, okay. In this case, I use row from row 7 to row 24, so it's going to be 18. We did it 18 iteration, okay, to adding it up, and with this you get this solution. Okay, this is a final solution by solving this subsystem, which only 20 even less than 30 constraint, 20, 25, 26 constraint problem. Okay, but this solution, when we put it in the working sheet here, okay, this solution here, it get the same optimum solution here. Okay, and once this solution reach the optimum, you can see that the maximum value become 0, right? Become non-negative, become non-positive, and the row constraint number 6399 have no meaning because it's a feasible solution, because ax minus b is equal to 0 is possible. Okay, so there's no violation anymore in all constraint. Okay, so that's guaranteed. That stop the process as we mentioned to you here. Okay, we repeat the process until the value. In this case, it's less than or equal to, because we use b minus ax instead of ax minus b. Okay, so this is the illustration in the case when you have LP with so many too many number of constraints. Okay, you can solve it by this example that solve a sequence of a much smaller scale LP. Okay, what is the benefit of doing this is that you can, instead of you having a large scale problem, but actually you solve a sequence of small scale problem and end up the final solution. You don't have to solve a one really large scale problem, and but solve a sequence of smallest, much smaller scale problem, and they reach the optimal solution before you completely enumerate all the possible constraints. Okay, so that's about it about this script. Okay, we finishing up with uh, the idea of how to handle the linear programming with too many constraints and illustrate an example on Excel for you. Okay, so in the next script, certainly we're going to continue with the LP with too many variables with an Excel illustration. Okay, so see you in the next script.